Right, it's now 3 o'clock, start time. Glad to see some made it back. Okay. So back to these strings and compiler performance. Here we have a graph of versions of GCC, and we have Clang. This is where ABI 11 kicked in. So standard string became a small string optimized string. What we have is these are the one that I did, my small string optimized string, standard string, and there's something called GNU CXX string, which is actually small string optimized and came out long before standard string was small string optimized. And it wasn't copy on write either. So, generally, standard string, small string, optimized string made, well, I can't tell the difference between there and there. These lower lines here is where it is. But, interestingly, we look at Visa's string here, these blue squares, significantly faster when it's a small string than standard string. Interesting feature, GCC 5.3 with the old standard string, performance not bad. Up here, all of these, when it's up here, the compiler optimized out the test. That means I've got compile time strings. I'm in the good zone. I'm very, very happy here. It's a log scale, warning different scales from the previous graphs. So what we can see is, we'll ignore these ones up at the top. That's just good news. That's fine. Good news is no news. What's happening around here? Well, this is an interesting feature. GC 5.3 with the ABI 11, small string optimized, non-copy on write string. Performance appalling. Terrible performance. GC 5.3, in fact, you'll find the 5 series compilers will probably give you very bad performance. They just drop the ball there. 6.3 tends to recover the performance. Again, Clang, early versions of Clang, very poor performance. Interestingly, Clang doesn't do as well with optimizing out const expra with regards to these small string optimized strings. Apart from, for some reason, GNU CXX string, when it's a small string, Clang really likes. Clang really likes GCC code. Okay. Look, don't question, just accept, okay? But in general, we can see here very reliable performance across all the rest, pretty much the same. Rubbish. Doesn't manage these optimizations here. This line here, standard small string, optimized string. There. Of course, it's much lower here because, of course, it's copy on write. It's not small string optimized. So we're not surprised to see standard string rise a bit. Here, ever heard that folklore that adding symbols to your executable on Linux makes it slower? There's the test case. Can you see any noticeable performance effect? No. There is none. It's a lie. Again, another one of those urban myths that is just, sorry, it's wrong. What else about this graph? It's pretty flat. We don't see any general improvement of performance over time. Remember, this is GC 473. Those are newer compilers. It might be the same architecture, but they're not scheduling the code any better, are they? No. It's a little bit of a shame. Okay. Let's slice and dice it slightly differently. You see here, there we've got the constructor and destructor performance, so that's a pretty simple test. Let's create a small string optimized string initialized from a C string literal. Here let's look at the assignment performance. Again, pretty flat. Again, Clang seems to do a reasonable job with GNU CXX visa string. Clang, in this case, managed to optimize out. My heavily optimized, by the way, in this string on these graphs, yes, it's got memcopy opt in there. So it's got my optimized memory copy in there that apparently didn't give very good performance earlier. But when we slice and dice it slightly differently and look at how Clang works with it, it works slightly better. Now, again, if we look at here, standard string, likewise we see relatively poor performance, which has improved considerably. We're moving from about there to up there. Remember that this is a log scale, so we're moving from about 10 to 7 to 10 to, what was it, 10 to the 7 to, what was it, say 5 times 10 to the 7. So it's a significant performance improvement to use the standard string. But it doesn't take much effort to write your own that can be just optimized out. Let's look at replacement. So I assign a string, but now what I've done is I've constructed a small string, initialized it with a small string, then what I'm going to do is replace it, assign a new small string into there, replace that. So I've got two potential mem copies going on. We can see clearly, it's not surprising that it can't be optimized out anymore because we've effectively got two mem copies going on. It's just a bit too hard, in quotes, for the compiler. Apart from bizarrely, remember I was slagging off GCC 5.3? Managed it there for some reason, but they've lost it over here. Why have the GCC crowd lost it again? Also, we see interestingly that Clang, quite a similar performance to the GCC crowd. Again, we can see GNU CXX vstring. It's doing pretty well. It's old code, that is. It's doing pretty well. Standard string, not too bad. Modern standard strings mirroring it reasonably well. You can't see the error bars on this because they're so small. I think that's enough from that graph. Okay. I mentioned about this fixed to MIT bits translator. So what does it do? It translates fixed messages from this binary format to this binary format and back. So it receives, it's a server, it listens to a socket, sends to another socket. Listens to another socket, sends back to the client. So we're translating from fix to this format and back again. So what happens is we're doing a search through the fixed message for little substrings, take a price, convert the price into a decimal, into a double, and then if we've got a quantity, take the quantity, which is an integer, convert that into an integer, so an integer string to a long, and then we're doing the reverse for coming back. So there's some searches going on, there's some string copies going on, there's quite a bit of F to A to F, A to I to A going on in there. I used Boostazio for my socket library. Why? It's easy. Turns out it's actually not much of a performance hit at all. Very, very heavily optimized, the code. extremely heavily optimized. I did not use Solar Flare or Exablaze cards because it's on my computer at home and I'd need to buy them. I didn't use Open Onload. That would have reduced context switches. It would have improved performance. Okay, so what is it? As I've mentioned, the details. I receive a fixed message from some kind of client, which is just pumping fixed messages at this. Translate it, send it over to a socket to a basic simulator, exchange simulator that I've written, which then sends back a fill message, and then that's translated back to a fixed fill message, sent back to the client. Time stops. So that's my timestamp, that round trip. I was using my computer for all sorts of things at the time, surfing the web, email, whatever. Sometimes it was quiet, sometimes it was busy, with and without NUMA control. I use Gen 2, even on my laptop. It is heavily optimized. I use the make-ops flag and the compar-C flags. They are long and extensive. I have a dual AMD 4180. Why? Because back then, it was a pretty decent processor. It's old now. It's got 2 memory paths buses on it. I've got a motherboard on there that makes sure it's 2 memory buses. It's got very fat FIFOs. It's a fast motherboard. It's run with performance profile enabled in CPU Freak, but it is particularly slow in SSE. Know your architecture. Remember that picture I showed earlier about the architecture? You need to know your architecture and get familiar with it. Okay. Older GCCs, newer GCCs. Here's Clang over here. These are Clang. We see the error bars. 4% mean average deviation is what I'm trying to aim for. Sometimes I couldn't get it. We can see older code, newer code, micro-optimisations being introduced. Sometimes they did really bad things. Sometimes the compiler, remember GC5 series, was just rubbish. What we see here is...
Sorry, what's on the y-axis here?
The y-axis is mean round trip in microseconds. Okay. So what we see here is, what I've done is I've timed the simulator that I've got, my exchange simulator, and then I've timed the whole link, the time taken for a fixed client to send a message to my link, for it to translate it, send it to the simulator to the exchange, sends back a fill, it translates the fill, sends it back to the fixed client, time stops. That's the full round trip. So if we subtract this number from this number, we can see the time for the translation back and forth without the time for my simulated exchange. So that's why this graph is included. We can see interesting features here. As I said, tends to get better as my micro-optimisations kicked in and I did more work and sweated harder. So we've gone down from about 85 microseconds. Down here, we're hitting 55 odd microseconds. Yeah, it's not bad. It's okay. I'm happy. Sadly, newer GCCs, really bad performance. That's curiously not in the simulator, the link, the exchange simulator. Remember, the exchange simulator doesn't have much in the way of optimizations that I've done to it. And we've seen that sometimes these micro-optimisations can play havoc with the code generator. And sometimes we've seen that the compilers are just rotten. And what we've got here is we can see the performance is quite poor for GCC 7 and 8. Curiously, 7.1 was okay, but 7.2 it really dropped off a cliff. Higher numbers are bad here, lower numbers are better. if we look at the actual simulator itself, the exchange simulator, I mean, look, the performance is roughly flat. And that's because, of course, I haven't put much effort into it at all. It's into here that I'm interested, the actual link itself. We can also see why the error bar is smaller here. Because I really wanted to find out, is this true or not? So I went from 4% mean average deviation to 2% mean average deviation. What happens is I send about 100,000 orders through this round trip and time how long it takes for 100,000 to happen. Divide the total time by 100,000. That's the time for one round trip. Then I repeat that between 5 to 10,000 times to get my mean average deviation to settle. So this is very heavily statistically measured to try and get reliable results. But remember that, of course, if we look at this, this is about what? 55 microseconds on an ancient architecture. The basic point is that all that effort to get these micro-optimisations in was wiped out by bad choice of compiler. Flip side of the coin, Clang is now as fast as GCC. Or is it GCC is as slow as Clang? The generated code, I mean. Shame. Clangers. I've been knocking Clang a bit. So let's be positive. This is how long it took to compile that software, that fixed to MIT bit translator. Wall clock time. Time, make minus J3, go. GCC 7, GCC 8. Over 35 minutes to compile that code. It's very, very slow. The main reason is Boost Hannah. If you want to be glacially slow in compilation times, Boost Hannah is way to go. Boost MPL is much faster for it to compile. Clang, on the other hand, crikey, just over 5 minutes for the same code. Hang on, that's 7 times performance difference. And what was Bjarne saying about modules? Ooh, I hope it's going to be about 8 times. Sod modules. Just use a better compiler. And remember, now, GCC 7 and 8, the performance of the generated code is just as rubbish as Clang. Yeah? Use Clang. Yeah, sorry, just as rubbish as? Yes, I'm being deliberately provocative because I do hope that some of you may even be Clang developers or may know Clang developers and say that arse Jason was being really nasty about you, and they'll have a look at this and they'll say, you know what, we're going to have at him, right? We'll show him, slag us off in front of loads of people. Yeah, we'll make it faster. Oh, boo hiss. Oh no, I'm so sad. I look so silly now. No, I've just got faster code. Brilliant. That's what I'm doing. This is heavily templated code, by the way, as well. So, and there's no error bars on this. I ran it a few times, but when I say a few times, it was 3, 4, 5. Actually, no, that's a lie. I actually did run it over a day, didn't I? Yes. No, just look. Mark 1 eyeballed the results and said it looks about that. And I was busy surfing the web and doing emails and God knows what. So the machine certainly wasn't quiescent. But I didn't bother to put error bars because it was massive, massive performance difference in compilation. Sorry, Clang. Getting code. This is about 100,000 lines of code in this library. Probably about 50,000 lines of code dedicated to this translator. So it's not big, it's not tiny, but it's reasonable-ish. And trying to get it to compile with Clang. What a pain. Okay, libc execs, you'd say. Don't use standard, don't use GCC's lib standard C++. Why, you dummy? Use Clang's one. I'd have to rebuild all my third party and boost and everything to link against it. Life's just too short. Couldn't be bothered. So I thought, all right, I'll stick with lib standard C++ from GNU and take the pain from that and compile a bug in Clang in that file. There's a no except specification here for hash maps.
Is that a compiler bug or a defect report in core?
It's a compiler bug, because you see what happens is when you replace the no except here with just, oops, I meant to say no except false here, right? And take away this decal val in there, it works.
If I recall correctly,
It
that's
compiles.
a core defect report.
Is it? Oh, okay.
So
It works.
right, actually.
When I changed it to no except true, in the no except in the hash functor, sort of, there, oh, no, genuinely, pardon me, it is a bug in Clang. Ha ha ha, that may be a defect report. But it is a bug in Clang, because I had a hash that I created, a hash functor. And the functor, the function call operator in it, I put no except true. By brainwave, I was probably up late at night and had too much coffee and shaking a bit. I deleted no except true. I just deleted the true and put no except. And it worked. Parser error in Clang. Yeah. Wasted 2 days of my time. My time's infinitely valuable to me. And a lot of swearing. That's the error message I got that told me that you should delete the parenthesis true parenthesis. It's been edited to fit on the slide because obviously this is a template error message. It is, of course, at least 5K in size, but nowhere in it. Note, in instantiation of default argument for required here. No, it just went off on a drugs. The error message is when you try and get your code to compile, because you think, oh, well, Clang's so much faster at compilation, and now GCC performance sucks so badly. Oh, we'll just move to Clang. Yeah? It's not easy. Just because your code has compiled with multiple GCC compilers over the years, you will come across compiler bugs. And you will come across defect reports in libraries that have been around for years as well, as the gentleman has thankfully cleared up for me. Thank you. Okay, we've talked about software, but what about the rest? We're not using include OS here, we're not running on the metal, so there is operating system, and this is an ancient old hardware. So let's look what happens if we change the operating system. Common law has it that an operating system accommodates for about 2 to 4% of your runtime. Roughly, common law. I think you'll know what I think about common law by now. I don't believe it. I want to see the numbers, please. For my test case, it might be true in general, but for this specific test case, and your mileage may vary, I want to see what happens. So I thought I'm going to use Centos. I hate Centos with a passion. It's an appalling distribution, but unfortunately it's used a lot by banks and finance. Why? Because they're skinflint bastards and they like to not pay for anything. Red Hat, sometimes they do pay for things, and they pay for Red Hat. God bless Red Hat, particularly Jonathan Wakely and all the rest who work there. They do pay for, very good. It's a proxy because I don't want to pay for Red Hat. I don't want to pay for Scientific Linux, so I'll use CentOS. So it's a proxy for it. Ubuntu. We all have heard of Ubuntu. You get your laptop, you stick a Ubuntu ISO image in there, see if it works. 5 minutes later, everything's working. Screen brightness, Bluetooth. Bluetooth on a laptop in Linux, wow. Yeah, it works, printing, etc. Ubuntu. And then, of course, I'm a Gentoo user. Come on, Gentoo, come on! You gotta, yeah. I didn't use my main computer, I used another computer. I created a fresh installation that was... These are stock ISO images, so I did an unfair race, because obviously I'm a support Gen 2. This is heavily optimized, stripped down. No unnecessary rubbish on there. Basically, I just barely installed it, yeah? And couldn't be bothered to run the rest of the installation. So just enough to basically reboot my stock kernel and run that, my code, and that's it. You know, no fcron, pah. I laugh in your face. SSH, pah. syslog-d, sod off. Nothing, right? Really, I mean, this would be utterly unusable in production. I don't care. I want Gen 2 to win, obviously. You know, look, I work in the city, okay? If I was fair, I wouldn't work in the city. I used a newer computer, you'll be pleased to know. Finally, I've moved into the 21st century of computers, granddad. This is a single processor Haswell. It's quite a decent processor, actually. It's an X Games machine. The story behind it is long and amusing. Ask me in the bar. I overclocked it to 4.2 gigahertz, which is well beyond the thermal capacity of it. So if you run too many of the cores, as I say, compiling, it'll overheat and crash because it can't dump the heat fast enough. Yes, I know I'm burning the chip out. I don't care. I did not apply any firmware patches. Why not a Skylake? They're not so heavily tuned to HFT. By the way, this sentence is a quote from Intel. You'll find out why shortly. Again, no solar flare or open onload. And yes, they would have reduced any impacts, and they would have. But often in the city, they're so stupid. They often don't. They'll use a solar flare card or an Exablaze card, but they won't use the kernel modules that come from it. Why? Because the DevOps guys are so gormless that it's too hard for them to do that installation, or IT security say, oh, no, we can't have any third-party modules on this. Yeah, the tail wags the dog. What was that quote by Beria in the film Death of Stalin? Wish I could take them out the back and shoot them and bulldoze them into a lime pit. Anyway, so often it's not used. And often, of course, the kernels are either so old, because this is a merchant bank and they update things when they go bust, basically, that often you can't actually get a kernel module that will run on it. So, hence, often not used. Okay. Hit me with it, the figures. Yes, it's one version. I didn't try different versions. This is compiled with GCC 7.3. So it's not the greatest GCC compiler on the planet, but it's a fair test. By the way, the binary image that was run was identical. When I say identical, you know that option to change the bootloader that you can put into the image to change your ld.so? Yeah, I did that as well. So this is identical libc, identical libm, identical, that was my boot. It's in one directory, because I got my own ld.so in there, because I changed the run part, the DL loader path. Please.
Did you also consider to try this Intel Clear Linux distribution as part of the...
I'd love to if somebody would pay me. So yes, I didn't use the libc from the actual operating system. I hope you can see from this graph, there is considerable difference in performance. That 4%, 2 words. Male of a cow, fecal matter. Look at the massive difference in performance. The operating system I love to hate, Centos, early version of Centos, 6.9. 6.9 is very new for the city, by the way. Utterly awful performance. Same code, same hardware. Look at that. This is nearly as slow as my 2.6 gigahertz, crikey, 6-year-old Opterons. And this is a Haswell. Where is it? Where did I put it down? It's an iCore 7. Overclocks at 4.2 gigahertz. Astonishingly poor. Kernel 2.6. Kernel 3. 3 series kernel. Significantly better performance. Ubuntu. I tried the generic and low latency kernels with Ubuntu. If you look carefully and have the time, and I don't have the time, the low latency kernels are POS. Useless. Uniformly slower than the generic kernel.
But isn't this a throughput test?
This is just a wall clock, high performance throughput, and I'm looking also at latencies included because I wait for the next message to come back. Before I send a message, I wait for the message to return. So it's both throughput and latency. And just rubbish, rotten, useless, not worth the space it takes. And we can see, here we are, this is a comparison 3.10, 3.13 kernel, right? Ubuntu, sadly, boo hiss, is slower than CentOS 7. If we come to the newer 4 series kernels, 4.13 series kernels, so this is getting into this century now. You know, we stopped using stone tablets around here. It looks better. The big problem with CentOS here, deviations are terrible. So the reliability of it is very poor. Why? I didn't have time to go into all the details of what's wrong with the kernel, what's running there, what's causing it, blah-de-blah. Of course, Gen 2, it's about the same speed as Ubuntu, some of the best Ubuntus, about the same speed as CentOS, but it's really reliable. It does pay. Gen 2 is it's about 5% faster than the best of the rest. So that is materially significant in the city, but the pain you've got to go through to get Gen 2 working, of course, your mileage may vary. And of course, we can see there's considerable variation. Okay. What about the hardware? Because I've changed the hardware from something prehistoric to something new. What's the performance difference there? Well, not surprisingly, pretty radical, right? We're looking at about 75 microsecond round trip down to a 22 microsecond round trip. On an iCore 7 4790. Yes, I did have hyperthreading enabled. Why? Remember that L1 cache? The L1 cache is shared between hyperthreads. And that means I don't have to wait for the L2 cache for data. I can share it between those as long as I know. Remember that I send a message, wait for the reply. So I'm chopping and changing between 2 threads. So that means that essentially what's going to happen down those 2 hyperthreads is one hyperthread is going to be used for the send, and then that'll be idle. Then it'll be used for the receive, and that'll be idle.
So this is one process?
This is one process running 2 threads. Yeah, there's no multi-threading here. Where's my queue? TCP/IP stack. The wire. It's too slow. Remember, this, if we're looking at 20 microseconds, subtract the time for that, which is about 7, so that's about 14 microseconds. Divide it by 2, that's about 7 microseconds.
Sorry. So this does this hit the wire at all?
I didn't actually. I just ran it. I ran it with ports on the local machine.
Yeah,
So it's running on the local stack, so it's not actually using a network card unless the kernel is really poorly written, which is unlikely.
One process with two threads in the same address space.
Correct.
Yes. Okay.
Yeah. As we expect. What a surprise. But notice, it's an equivalent to the impact in the choice of the operating system. Poorly chosen hardware can be just as bad as poorly chosen operating system. And what's even more interesting, hang on, remember that graph I had about how much effort I put into making it faster? Yeah, where I went from about 100 microseconds down to about 50, 70 microseconds for the GCC because it lost a load, right? So that's a 30 microsecond gain. 30 microseconds is what, from there to there? That much. Yeah? Much less than the performance I can gain in hardware choice. Much less than I can gain in performance of operating system. Okay. We've all heard about Spectre and Meltdown. I mentioned it earlier. And it's been in the bladders in March this year when it surfaced in the register. So let's have a look and see what happens to these operating systems and the performance of this code in the face of Spectre and Meltdown. Remember, basically what I'm doing is I'm doing a socket read and a socket write. So this is a kernel transition, but it's a really simple kernel transition, and I'm not doing lots of other things as well. I haven't run strace on this, so I don't exactly know, forgive me, I've only got so much time in the day. And I have to do this on weekends and in the evenings when my wife allows me to and doesn't try and distract me from doing things that she considers are much more exciting and intellectually interesting. So, caveats aside, here we have pre-mitigations and post-mitigations for evil CentOS 6.9. Look at the performance impact. Stunning performance impact. This is about 90 microseconds up to over 125 microseconds impact. Serious stuff. This, again, we can see is significantly less for the 3 series kernel. Yeah, you see, very carefully chosen kernels, and I ran a special checker to make sure that it actually did do what they claimed it did. There is still a performance impact here. It goes from about 21 to about 23 microseconds. And yes, look at the deviations here. It's statistically significant. Okay, CentOS. CentOS is evil and nasty. We don't like CentOS, so I don't care. Ha ha ha, it's badly hit. Ubuntu, I prefer Ubuntu. Oh dear. Oh dear, oh dear, oh dear, oh dear, oh dear, oh dear. Crikey. So we've got generic kernel. I didn't manage to get the post mitigations for it because it was just too much. I couldn't find the kernel for it, but the low latency I could find for it. Post mitigations, serious impact on the deviation. I just couldn't get it to settle. Ran it for about 2 days and it just wouldn't converge. Post mitigations for Ubuntu and 3.13 series kernels, terrible, 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 terrible. Look at the impact from 4.10 to 4.13. There's no 4.13 post mitigation or 4.10 post mitigation for Ubuntu that I could find, and I sweated to try and find it. And look at the massive impact in performance we get. This is just bonkers. And it's a genuine figure. It's not, I ran it for about a week to try and get, because I thought I'd buggered something up and what have you. No, really, genuinely. Genuine, serious impacts. Again, we look at newer kernels here, Ubuntu 17. And we can see significant performance impacts we get with Spectre and Meltdown. By the way, I was asked to do an endnote at Stack at the end of April. When the announcement for my endnote went out, which was about these figures, 4 minutes later, Intel sent me an email saying, can we have a talk, please? So then we arranged some time to talk to them and spent 2 to 3 hours being grilled by 3 people from Intel on the phone over these figures. And they said, we concur with your results, your findings, backed up by Intel themselves. Recall I run AMD chips? Did I mention anything about AMD getting in touch? Gen 2, of course. How's it affected? Statistically irrelevant. In terms of the simulator. In terms of the actual full round trip, statistically significant impact. Remember, on Gen 2, I can actually turn on and off the compilation options that mitigate against this. And I didn't apply firmware patches. I just used kernel mitigations, full Repline compiler for this. So we can see there is serious impact in performance that you're going to get. Fortunately, it doesn't have any effect at all on the actual the variance that you get in your latency, which is very, very critical as well. That we saw in other operating systems, we can see considerable variance in the latency. Again, considerable variance in our expectation. So, it's clearly complicated. There is nothing trivial about this. You've got to profile, profile, and profile again. You can see that those figures took years to build up. It's not a day, it's not a week. Time your critical code. Experiment with the moving parts of it. And you need a shed load of unit tests to make sure you don't break anything. Because, of course, you're trying to do less. You're omitting stuff. So you might have broken your code. And also, unexpected stuff happens. So you might think you've sped it up a lot, and your little micro benchmark might show, yeah, sweet, I'm 5 times faster. But you put it in the main code, just makes it worse for some bizarre reason. I hope you now realize that high-performance code is incredibly sensitive to the performance of the operating system and hardware. Choosing the right compiler is hard as well, and re-optimisations from, say, GCC to Clang are very costly without an extensive test suite. I have about 25,000 unit tests for this code. At last count, about 5 years ago. And they've only increased. And this is code I have at home, by the way. GCC 7 and 8, significantly slower than GCC 6. Again, the law on the street, much as I trust that, haha, it seems to be from other teams as well. They've noticed a performance degradation. Clang has a stable performance. The good news. The bad news is it's as slow as GCC 7 and 8. The good news is you can recompile your code faster. So for running these tests and tweaking. But the choice of operating system can have an equivalent impact on all the massaging you did over 5 years. If you want a sweet, quick fix for speed, buy a faster computer, put the correct operating system on, then massage the code. As I've said, select hardware, choose your OS very wisely. And no one compiler, one single compiler appears to be the sweet spot, sadly. The mitigations for Spectre and Meltdown are disastrous for performance. In fact, the actual mitigations for AMD are, if you use the firmware patch and recompile your kernel, turn off the branch predictor completely. There is no branch predictor anymore. There is no superscaler in your superscaler chip. You've now got a MIPS 10,000 pipeline, RISC pipeline. Centos and Xubuntu, Haswell chips and Intel chips are less badly affected. The kernel can turn on and off the branch predictor. So the branch predictor can be turned back on in user code, turned back on in kernel code, and turned off during the transitions, the dangerous time. So you'll get less impact from Haswell's. I wonder why AMD didn't want to get in touch. Again, verify performance impact. Verify, verify. You might say firewall. I say dangerous. Fixed messages are ASCII messages, and we've never heard of a buffer overrun from ASCII messages, have we? If you want the references, here's the references for all the stuff I've done. The library that I've got up there that you can have a look at. Yes, I'm old school, it's SourceForge. Why is it not on GitHub? Why change? Can't be bothered. Interesting paper about switch statement performance. Branch prediction and static branch prediction. Gentlemen, thank you very much.
So if I would be so inclined to play around with this stuff at home, perhaps with another operating system, is that fixed simulator? Is that something?
It's all LGPL.
Okay, yeah. So I can get that's interesting.
Help yourself. You can download the source code from SourceForge. I use Jenkins to create packages and release packages. Yes, I went through the pain of trying to work out the SourceForge file release system, which I managed to hammer it, so my releases happen automatically. There is Doxygen-based documentation for it of extremely variable quality, because I wrote it. I know it's bad in many, many places. If anybody's got any suggestions, I'm more than welcome to hear them. I'm not precious about this code at all.
If this is like a billion-dollar industry, have you thought about making your own compiler?
I'd love to. I'd love to if I had the time.
Optimize it for high-frequency trading?
I would love to, but it's, yeah, time, sadly. I need a job, paying job. I come here and I don't get paid because I'm a contractor.
But
And
the business in general?
the problem is banks seem to have the impression that writing their own custom languages is a good idea. Please.
Yeah, I believe that the compilers have some sort of inbuilt cost model for deciding what kind of instructions to implement.
Yes, they do.
So I would suspect that some of the variabilities could do tweaks to that cost model between compiler releases.
I would say that there is, the gentleman says the cost model in compilers. I absolutely agree. There is a cost model in the compilers. I would go further to suggest, hazard a suggestion, a speculation that the cost model is imperfect.
Yeah.
And has been for many years for certain architectures.
The question then is, have you looked into this cost model and tried to tweak it yourself and build your own cost model?
No, I haven't. Again, sadly, it's a matter of time. I'm sorry, this is my excuse. It's a matter of time. I do this at home as a hobby. And some people watch TV. I program as a hobby. But that means because I work at the city, I tend to get to work at about 9:30 and leave work at 7:30. After you've had dinner and said hello to the wife, that gives you about an hour in the evening before you go to bed. And the weekends are taken up usually with doing what Madam desires. So yes, I'd love to be able to spend more time with this. And yeah, a very good point regarding the cost models. Correct. And again, regarding compiler. Thank you.